Right, in this lesson, we're going to learn about electricity, real basics, like the real basic stuff. Nothing in depth here. If you'd like to know more, you can read more in your Pearson, or you can go and look some of these ideas up. All right, first one, I want you to write down words which you associate with electricity. I should get at least 5. I would expect a lot more. Right, we have to start right from the beginning. We have to talk about atoms to start with if we want to understand what electricity is. We have to look at our atomic model. So we've got protons and neutrons in our atom nucleus. And we also have electrons moving around the outside. Now, they're going really, really fast. So we'll learn more about them later in the year. We have to be able to understand that this is what's going on inside each atom. Sometimes you see it drawn like this, but it's more closely resembling this, that has heaps and heaps of electrons just whizzing about all over the shop. They're not moving in these nice little shapes, they're whizzing about. The electron movement is what creates electrical charge. Okay, so if we suddenly have electrons that are able to move away from the nucleus, and they can in a metal atom, which makes metal wires really good for moving electricity, then these electrons can flow freely, and if they all go in the same direction, we can have that current flowing through an electrical wire, for example. Let's talk about static electricity, and what it is a build-up of electrons, or that negative charge. Because if we flick back here, these electrons have a negative charge and our protons have a positive charge. So it's all about negative and positive charges. So you often see an experiment where a rod is rubbed on a type of cloth, it might be like a microfiber cloth, and all the negative charges, or the electrons, jump across to this cloth. And what happens is it makes this very negative, it makes this very positive, and therefore this charge is ready to zap you. And that's what happens. As the electrons jump back, energy is converted into heat, light, sound, and even kinetic energy. So you might see if you get a bit of a spark of electric shock, and it's happening now that the weather is really dry, and you touch something metal, all the electrons are on you and they're jumping back there to the positive charged metal, and you might see an actual spark. You'll feel it, and you might see a bit of light and sound and heat, all those kinds of things. This is a really good simulation to show what is going on in this situation here. Okay, so we've got this balloon, we're going to rub it on the jumper, and you can actually see that it starts to pick up the negative electrons. You can see because it's got all those negative ones, it's actually very attracted to the jumper. It wants to keep going back and forth. And if we go over here, it's actually repelling the negative charges. And that's exactly what's going on when you have something that is picking up all those electrons. Okay, let's go back to here. Okay. The electrical current is what happens when the electrical charge moves and the flow of electrons happens. It's pushing that negative current down towards an area that is positive. In a simple circuit of electrical current, what we have to have is an energy source. So in this case, it's the battery. We have an energy user, so the thing that's going to take on the current and use it wisely. So in this case, it's the light globe. And we also have wires that connect things up. In this particular one, you also have a switch that turns it on and off. So if you don't want the light globe to glow, you can open up the switch, which stops the circuit, which stops the electricity flowing all the way through. We will actually have a go at making these, and here's a more realistic version of what we're going to see. A switch that looks like this. We've got those connecting wires, little alligator clips connecting everything up. Here's our energy source, and here is our little light globe. Our circuit diagrams can be drawn. If you aren't a particularly good drawer and you can't really depict this very well, we've got scientific ways of doing that. So we can say, here's our energy user, here's our switch, it's open or it's shut, and here's our connecting wire and all those kinds of things. So here's our energy supply. Here's a torch. This is straight out of your textbook, and it's got, here's what the torch would look like on the inside. Here's a simplified diagram, and here's what our circuit diagram is showing. This is where our battery is, this is where our energy is coming from, and it's flowing to the energy user or our light globe. It's got a switch that can turn it on and off. In this case, it is open, which means the electricity cannot flow through the whole circuit. It's not able to get past this part, but if we close this little gate here, it can continue to flow. So that's what is going on when you turn your torch on and off. All right, we have two different types of circuits. In this one, we've got 6 volts of electricity, and we'll talk about what this means later. So a bit of energy is flowing around the system. It's going through 2 light globes. And you can see the 2 light globes are stacked up in a row. And what that means is they have to share the current. They have to share the voltage and share the energy going through. So in actual fact, these 2 light globes will glow at 3 volts. And if we took one of them out of the system and we just had the one, it would glow at 6. So it would be twice as bright. So the way we can fix that is to hook things up in parallel which means our electrical current is going to flow all the way through here and give it 6 volts, and it's also going to flow all the way through here and give it 6 volts. All right, so if we stack them up one after the other, it's almost like they have to share that energy. If we stack them up in their own little circuit, then they get the full current. So we've got the 6 volts shown here and the 6 volts here. Right, I would like you to talk about Christmas lights. Christmas lights are the perfect example of a parallel circuit. I would like you to hypothesize why having these lights wired as a series circuit would be a bad idea. This is our series, and this is our parallel. So talk about the Christmas lights. Right, measuring electricity, we talk about current, which is how much charge is flowing. So if it's really fast current, it's like a river running really fast. There's a lot of electricity going through, and we measure that in amps, so basically how fast it's going. We also measure voltage, which is how much energy the electrons are carrying. We have to think of those electrons moving around like a little electron with a bucket. It's carrying some energy and it's flowing really, really fast. If it empties its energy out into, say, an energy user like a light globe, then it has less energy, but it can still be flowing quite fast. We measure voltage in volts. We also talk about resistance, which is how easy it is for the electrons to flow through the wires. We have a look at this little image. The voltage is the energy it's trying to push to make this go faster, and the resistance is up here, and it is trying to slow everything down. So current, we have to think about it like that water. So think about it like that river running, or in this case, the tap. We can have a very, very slow current or a very, very fast current, allow that electricity to flow quickly. When we talk about voltage, we might go to a different country and find that the plug in the wall puts out a different voltage. So here in Australia, every electrical socket is putting through 240 volts, but your poor laptop can't actually handle all that voltage or that energy in one go. So it has to use this transformer, which drops the voltage to something it can manage. It can still hold on to a little bit of energy though, and just convert it or transform it into something else. Resistance is about kind of kicking the hose. That's why I really like this picture. It shows that there is resistance in letting those electrons flow through, and there might be many reasons why there is resistance. Might be the type of wire, might be the metal that it's being used. And we see resistance can be used in a good way. The metal that is used in a light globe is actually resisting the flow of energy so much that the energy starts to come out as heat and light energy, and that's why we start to see that light globe glow. This is a multimeter, and we'll be playing with these later in the week, but these are what can measure your current and your voltage. They're quite complicated, so when we come to use them, we'll have to make sure we are reading the correct scale there. Right, I would like you to figure out if you've tripped the circuit at your house, what occurs when this happens, and why does this happen? Right, some wiring safety. Materials covered in insulation material. We know we've got coloured wires around the outside. Otherwise, what happens is the electrical flow, or the electrons, can actually jump out and go in other directions. So we need to kind of use that insulation to keep it all in, just pushing them down the wire. We have 3 main wires. If you crack open something that plugs into the wall, we have an active wire, it's brown. We have a neutral wire that is blue, and we have an earth wire that is the yellow and green stripe there. Now, the active wire is what is actually flowing towards the thing that you're using the energy for. The neutral wire has the energy going the other direction, or pushing the electrons back to go and pick up the energy. And the earth wire is there to offload any excess charge that may be there and keep you safe, so it doesn't actually jump out and zap you. Some things have an earth wire, some things don't. So you might find plugs with just these 2 up here and not the earth wire. Circuit breakers, they react to higher than normal current by switching off the circuit, and what they do is exactly that. It says, all right, I can detect a huge amount of current and that shouldn't be there, so I'm going to be really safe and turn everything off. You might see one of these in your house. Safety switches are also now getting more and more common on PowerPoints. I want you to list many kinds of batteries as you can recall. Right, we can store electricity in portable ways with batteries, and we can use wet cells. So a wet cell might be an example that you see as a car battery, and they use some electrodes in a flowing liquid to push the electrons through. We can use dry cells, and they're our more common batteries that we use. And instead of using this liquid, they actually use this dry paste. They are still pushing the electrons through this dry paste from one end to the other so that the electrons can flow. And we also have photovoltaic cells or solar cells, right? Our solar cells are the ones that we see in our panels on our roof. So that cell is just that one section. It then gets stuck with a whole bunch of others and then put on your roof with many, many of those. Solar cells work by knocking electrons from the silicon crystals that are in the cell. They knock them off. Once we then collect all those electrons, we can flow and it creates a charge. So the sunlight is actually high energy, the radiation pushes off the electrons and we can catch them essentially and use them for what we need. And that might mean powering our entire house. All right, I want you to make sure you finished all the quiz questions because I will be marking them.